Hello there. Good evening and welcome back to Astroveo's Continuing Education Series, where this evening we are going to be talking about myths in astronomy, so astro myths. So these are some topics that are really dear to my heart, and Joseph's, I know Joseph's not available tonight. I do apologise. He's busy doing other astronomy things out there in California. So you've just got to put up with me from a very snowy and cold Massachusetts. And what we're going to talk about is some common myths in astronomy that people have about the night sky and the daytime sky. And it's one of those things that you only hear about when people talk about it, or because we're astronomers, we get a lot of people that say, hey, what about this? Or did you see that in the news? And so I thought we'd actually just chat through a few things. One of the things that's really nice, and I had my very young son, Beaumaris, do this a wee while ago. This was Beaumaris this is probably 3 or 4 years ago now, when he was a fair bit younger, maybe 5 years ago. He did the phases of the moon as a school project, and he did it with Oreos. And as you can see, he had the most delightful time, because every time he had to change the phase of the moon, he got to eat a bit of the Oreo biscuit. So he was very, very happy with that. But he really enjoyed this project, and we talked about how you can see the moon during the day, during the night, and it goes through different phases depending on its position. So he had a really yummy way of learning about the Earth, Moon, Sun system. So I just thought I'd throw this up for Beaumaris. We talk about these Astroveo podcasts quite often. He gets all excited, and I promise he'd be in this week's. Okay, let's get going. So let's talk about some common everyday myths in astronomy. There's about 5 or 6. I can't remember how many I put in here, but there's a few. One of the biggies is that the moon only comes out at night. Now that is a myth. You can see the moon during the day. It is illuminated sometimes during the day. And I think people think that the moon only comes out at night because, of course, the nighttime sky is quite dark and the moon being illuminated by the sun is quite bright. And so very naturally, it's very noticeable. During the day, the moon is quite a bit less noticeable because, of course, you've got the daytime sky being illuminated by the sun, and so the moon is proportionally appears less bright because it's contrasting with the bright sun. Now, the way to think about it is here, you can think about where the sun is in its position. Now, there's this very nice graphic, but it's somewhat complicated, so we'll go through it maybe a little bit carefully. So the Earth is in the middle, this blue, what looks like a blue marble. And then you have the moon sort of orbiting it, and of course you have on the very outside you have the various sort of shapes of moon that you see in the sky, the various phases. And this diagram is assuming that the sunlight is coming in from this direction, and in fact you can see here it says direction of sunlight. And I just realised I'm pointing to the screen and you can't see me doing this, but essentially, at least from the way I'm looking at it, the sunlight's coming in from here. Now, think about a new moon. Now, a new moon is when the Earth, Moon, Sun system is almost perfectly in alignment. Not perfect, because that would be a solar eclipse, but it's very close to being in alignment, so you don't see anything. That's what a new moon is. And then a day or two later, you get a very thin crescent moon. So we're now sort of in the top right part of the diagram here. So as the moon orbits the Earth, it's now moving into the first quarter, and you get this thin crescent. Well, thin crescents are of course, always visible in the first quarter just after sunset. So the sun sets, and then you'll see this very, very thin crescent. So if the sun is here and it's going down, where's the sun? Hang on, I'll get my hands right here. There's the sun. No, it can't be that way. The crescent must be this way because the sun illuminates this side of the moon. So you see this very, very thin crescent, and then the sun sets, and then the moon sets. Well, as the phase is increasing, that's called a waxing moon. Essentially, the moon appears to be getting brighter and brighter. That occurs during the night. So from sunset through the night, on successive days, the moon appears to be getting more and more luminous, until about 14 days after a new moon, you get a full moon, and a full moon rises as the sun sets. Well, then if you take that further, we're now down in the bottom left of the image here. You then you go from a full moon to a gibbous moon, which is about a 3/4 moon. But that starts to occur later and later. So if a full moon rises when the sun sets, the waning moon, where the phases appear, the moon appears to be getting less and less bright, that occurs later and later during the night, which means the moon ends up being up during the day. You get to see it during the day. And so as you go toward a half moon in the third quarter, that rises about midnight. And then it's available for approximately 12 hours. So a last quarter, a third quarter, half moon actually sets at 12 o'clock midday the next day. So it rises about midnight and it sets about midday. So yes, you can see an illuminated moon during the day. It has to be in the third quarter, the last quarter. So you're typically seeing a waning moon. A waxing moon is seen at night. A waning moon can be seen through the later part of the night into the early morning. So yes, you definitely can see the moon in the daytime. Okay, so we've done that one. That's a great one. So here's perhaps possibly the most common myth in astronomy, is that the changing seasons are caused by the fact that the Earth's distance changes relative to the Sun. Now, is that true? Does the Earth change distance to the Sun? And the answer is yes. Now, we've discussed this on several of our previous podcasts. And in fact, just recently, where are we now? We're early February, but Beaumaris just had his birthday, actually. Happy birthday, Beaumaris. About a month ago, the Earth was closest to the Sun. Well, here in the Northern Hemisphere in Massachusetts, it's been very cold for the past 2 or 3 weeks, near or below zero, the freezing point of water. So what that means is, even though we're very close to the Sun right now, it's still very cold in the Northern Hemisphere. Of course, in the Southern Hemisphere, it's very warm. So that's all already giving you a sense of something funny going on, because we're talking about Northern Hemisphere, Southern Hemisphere. Now, why does the Earth change distance relative to the Sun? That should be a perfect circular orbit, right? Well, that's not true. The Earth's orbit is slightly eccentric, which means it's very, very slightly like an egg shape. Now, I'm exaggerating here, but it's a bit more like that. It's a slightly flattened circle, which means there are times when the Earth is slightly closer to the Sun as it orbits, and then sometimes it's slightly farther away. It just so happens to be closest to the Sun in January and farthest away in July. June, late June. So what does cause the seasons? Well, it's actually to do with the Earth's tilt. Now that gives us a hint, right? We had a hint this was correct, because as I said, it's very, very cold here in Massachusetts at the moment in Northeast America. And of course, in the Southern Hemisphere, in Australia, South Africa, New Zealand, for instance, it's really quite warm. It's their summer. And that is being caused because as the Earth orbits the Sun, if here's the Sun and here's the line with the Earth's axis is not straight up and down like this. The rotation axis is actually tilted by about 23.5 degrees. What that means is that during, where would this be now? This would be, well, let's do it, where my hands are. This would be if this, here was the Northern Hemisphere, this would actually be in the summer. Because what happens is the Northern Hemisphere receives an awful lot of sunlight because the Earth is tilted toward the Sun. So the North Pole, the Northern Hemisphere here, gets an awful lot of sunlight. The Sun's high in the sky, and it's the Northern Hemisphere summer. Well, in the Southern Hemisphere, which would be down here on my hand, due to the angle, the Sun is quite low in the sky, so you get the Southern Hemisphere winter. Well, conversely, sorry, go get my hands right here. Conversely, 6 months later, the tilt is now here. The Southern Hemisphere gets a lot of the sun, and the Northern Hemisphere does not. So what's happening right now it's early February in the Northern Hemisphere, we are still tilted away from the Sun a fair amount. So that means the Sun isn't in the sky very long. The Earth isn't being heated by the solar rays, which then heats up the air, which makes it nice and warm. But in the Southern Hemisphere, the tilt of the Earth is at such a point that it's really facing the Sun, and so the Sun is high in the sky. You get a lot of heating of the ground heats the air, so you get a summer. So the way to think about it is, you see here on the graphic here, from a nice really graphic put together by Adrian Dean, is on when it's farthest from the sun. So you're looking at the left-hand side of the graphic here. This would be shortest night. Hang on, let's make sure I get this right. Shortest night, longest days. That must mean it's about June 21st. So you get a northern hemisphere summer and a southern hemisphere winter. As you come toward the middle of the diagram of the graphic, now you're saying you get equal lengths of day and night. Well, that happens twice a year, once on the solstice in spring and once on the solstice in autumn. So the vernal, no, wrong way around, got the wrong word, the equinox, sorry. So the vernal equinox, the spring equinox, is about the 20th, 21st of March. The fall or autumnal equinox is on about the 20th, 21st of September. On those days, you get the same amount of day and light across the Earth. You get about 12 hours of daylight, 12 hours of nighttime. Conversely, on the right-hand side of this graphic, you can see the longest night in the Northern Hemisphere, which is about December 21st, more or less. That's when the sun is nearly closest to the sun. The Earth, sorry, is nearly closest to the sun. You can see that on the graphic. It says perihelion is about 147 million kilometers from the sun. Well, on the left-hand side, it says aphelion, as far as it can be from the sun. It's about 152 million kilometers. So there's actually a range of about 5 million kilometers. That's actually not very much. That's about 3.5–4% of the total distance. So it really isn't to do with distance in this case. It's actually the axial tilt of the Earth. Now, 5 million kilometers for humans, of course, is an enormous amount. You couldn't run that in a year, for instance. It's a big, big number. Now, in terms of very far away stars, depending on how far away they are, that does actually change their brightness enormously. And we're going to talk about that shortly, actually, one of my other astro myths coming up. But for here on Earth, as Earth-dwelling inhabitants, we don't notice that 5 million kilometers very much. What we do notice is the axial tilt changing, or the relative tilt for each hemisphere changing. That's really what causes the seasons. So if anybody says to you, hey, yeah, it's cold this winter, we must be farther away from the sun, it's actually the opposite. We're actually closest to the sun in January, February, and it's still cold in the northern hemisphere. So that's a good sort of disproof of that myth there. All right, so let's move on. So this is one of my favorites, and I think we're going to talk about this in terms of what I just said, in terms of distance of stars being away from the Earth. What does that really mean? And a lot of people think the North Star, which is a star very close to the North rotational pole in the northern hemisphere, there's this sort of myth that it's the brightest star in the night sky. Now you have to be very careful with your wording here, because if you say it's the brightest star in the sky, not the night sky, of course the brightest star in the sky, is the sun, because it's closest to us. It's on our doorstep. It's only, as we just saw, it's about 150 million kilometers away from us. But there is this myth that the North Star, that does help you find the direction north in the night sky, and that it's the brightest star in the sky, and it's in the night sky, and it's really easy to find because it's so bright. Turns out it's actually not the brightest star in the night sky. It's quite faint, actually. It is visible under dark skies, but if you're in the middle of a city, for instance, and I live about 30 miles north of Boston, it's quite tough to see if you're in Boston. However, if you're in the countryside, or there's a really nice little national state park just up the road from me called Halibut Point, if you go into that state park and you look out toward the Atlantic Ocean looking east, or northeast in this case, you can actually see Polaris, the North Star, quite easily. So I'm going to show you what we mean by that. So the brightest star in the night sky is actually a star called Sirius. And Sirius is, I'm going to show you how to find it. It's actually, if you're in the northern hemisphere, or even just slightly south of the equator, you can see Sirius quite nicely by following the belt of Orion toward which direction would it be? It would be slightly southeast, actually. And so here's the constellation Orion. You can see here in this really nice graphic from earthsky.org. And this is the sort of basic outline of the constellation Orion. And these three stars are Orion's belt, and if you go down toward the southeast, you'll find this really very bright object, and this is Sirius. That is the brightest star in the night sky. And what the reason why people the reason why we can perhaps think of why Polaris is not the brightest star is we need to understand a little bit about these star systems and what's really going on. So another name for the North Star is Polaris. It's also called Alpha Ursa Minor, because Ursa Minor is the constellation in which it resides, and Alpha means it's the brightest star in that constellation. So it's Alpha Ursa Minor. It is actually a triple system. It's quite interesting, actually. It consists of 3 stars in total. There are 2 stars orbiting each other here and here. So there are 2. They're called AA and AB. Those 2. So these 2 orbit like this, and then there's a 3rd star, the B star, that's orbiting these 2. So it's a really quite interesting system. Now, these stars are made up, if anybody knows, any of our listeners, our three viewers, as we talk about each week, if any of our 3 viewers know much about stars, they'll all automatically be able to see that the spectral types of these stars are F7, and I'll come back to the 1b in a second, F6, and F3. So all 3 of them are F stars. However, here's the really interesting part. The smaller and less bright star in the binary, the 2 stars orbiting each other, these 2, is the F6V, and the V stands for dwarf. Now, dwarf doesn't mean necessarily it's small. It's sort of, dwarf really means that the star is on the main sequence, as we call it for astronomy. And the main sequence really is the very stable part of a star's journey. It's essentially the stage of its life where its gravity that wants to collapse it up is balanced by the radiation pressure pushing it out. So it's a very stable system. The surface, it stays the same size, more or less the same brightness. So that V actually means dwarf, or it's in this sort of stable part of its life. Well, let's go back to the star AA in Polaris, this triple system. It's an F7. Now the 1B, 1 actually stands for supergiant. And B is a sort of type of the type of supergiant it is, the type of chemicals it has in its atmosphere. But a supergiant, as the name might suggest, is not only is it a giant star, it's a supergiant star. So it's very, very puffed up, which means it's in the later stages of its life. It's about to really sort of cease being a star. I don't will the star go supernova? F7. Yes, it probably will. This will become a supernova. I don't know, well, how long, what's the lifetime of a supergiant? Couple of million years. In the next million years or so, it's going to become a supernova. But supergiants have this other nice property of, if it was an F7 dwarf, its size might be like this. So it gives off a certain amount of light for its surface area. Well, a supergiant is ginormous, almost as big as the radio dish up at Haystack Observatory behind my head there. The surface area is absolutely enormous. So what that means is that supergiants are very, very, very bright. So if I'm saying the supergiant is bright, and there are 3 stars there, why isn't Polaris the brightest star in the night sky? Well, we need to look at the properties of the real brightest star in the night sky. It's called Sirius, or the dog star. And its a sort of official name is Alpha Canis Major. It's in the constellation Canis Major, which is the great dog, and Alpha again is the Greek letter, the first Greek letter of the Greek alphabet. So it's the brightest star in that constellation. For those of you who are interested, Ursa Minor, by the way, means the little bear. So that's the constellation that Polaris is in. Well, Sirius is a bit of an interesting system because it itself is a double system. Now it's the brightest star, the biggest star, the bigger and brighter star is an A0, and it's a dwarf. So again, it's very nice and stable, sitting there on the main sequence. Now remember that is where the gravitational sort of urge for gravity to collapse the star up is nicely balanced by the radiation pressure, so the star stays nice and stable. Now, we talked about Sirius before in a previous podcast. A0, an A0 dwarf, the V, is actually a very specific designation for Sirius, and by definition, it's 10,000 degrees. And the reference star that we put all these spectral types to, including the temperatures, is actually Vega, which is Alpha Lyrae. But the primary star for Sirius is one of these 10,000 Kelvin stars. It's A0 by definition, actually. It's a formal definition. Its spectral type is A0. And what it means is the brightness in all the different coloured filters that we use in astronomy is identical. So that means its B minus V colour is 0, its V minus I colour is 0, its V minus 2 mass J colour is 0. But that means you get equal flux at all wavelengths. So the star is actually sort of pure white. So that's the sort of very definition of a 10,000 Kelvin star. Well, Sirius has a second star, so there are two stars orbiting each other. Sirius B, the second star in the Sirius double system, is actually a white dwarf of a classification DA2. So this is a very, very hot white dwarf. It's probably, depends on its age actually, and I don't know the age of the Sirius system, but you're probably talking like a 30,000, maybe 50,000 Kelvin star. But don't forget, a white dwarf is basically the stellar remnant of an old star that became a giant. So we know that this system has two stars, but there isn't a supergiant there. So the Polaris has three stars, one of which is a supergiant, and Sirius only has two stars, one of which is a very, very small white dwarf. White dwarfs are tiny, so they don't have much surface area. So how the heck is Sirius brighter than the Sirius system? How is it brighter than Polaris? Well, there's only one possible answer. So either something is blocking the light from Polaris, or the Polaris system is much, much farther away. And that's the correct answer. It turns out Polaris is about 446 light years from Earth, from the sun. And don't forget, a light year is the distance light travels in a year. So it's some ginormous number. I can't remember the number off the top of my head, but it's billions upon billions upon billions of miles. And so Sirius, Polaris is 446 light years away. Sirius is on our doorstep, figuratively speaking. It's only 8.6 light years away. It's about twice as far as the next nearest star after the sun. So even though there are three stars, one of which is a supergiant in the Polaris system, so you think if you added the flux or the light from all three stars, it would be super bright. It is very bright, but it's very, very far away. Sirius, while it has two stars, one of which is pretty dim, the white dwarf is very faint, it's the brightest star in the night sky because it is so very, very close to us. And so that's the key there. So the myth that the North Star is the brightest star in the night sky is actually not true. It's Sirius, the dog star, or Alpha Canis Major. And again, you can see by the graphic here, you can find that by just dropping southeast of Orion's belt. So very, very easy to see, but I saw it just this evening. All right, well, spend a lot of time on that one, but that's a really important one because there's a lot of astrophysics in that question, actually. So here is another big myth, and I think I thought this when I was younger. Sorry, I'm going to have some tea. You know, the British and their tea were always supping away. Now, you might say to yourself, why do you think Mercury might be the hottest planet? Well, we know, of course, that Mercury is the closest object to the Sun, closest stellar object. So I don't know if this graphic is coming up on the recording. I hope it is. But here's a graphic of essentially the Sun, Mercury, Venus, Earth system, so the inner planets. And we can see that Mercury is very close to the Sun. It's the first planet, and then Venus is next, then Earth, then Mars, and these are the relative distances. Well, given that Mercury is so close to the Sun, it's a very natural thing to assume that it would be the hottest. The person sitting closest to the campfire feels the warmest. Okay, so I want to go back to the main presentation. So here's it's a beautiful image. This is a real sort of a real color composite image of Mercury that are by various NASA spacecraft, and you can see this beautiful pockmarked world, all these craters and all sorts going on here. So this planet, the Mercury, has been bombarded by asteroids and meteors in the solar system. Well, the Mercury Sun distance is not very much actually. It's only 0.39 astronomical units. And remember, the astronomical unit is the mean distance of the Earth to the Sun, which turns out to be about 93 million miles. Well, the mean distance of Mercury to the Sun is only 36 million miles. It's about a third as close as we are, roughly. Well, let's look at Venus. This is a real NASA image of Venus. Again, wonderful sort of flat Earth, anti-flat Earth statement here, with the two most inner planets being round, which is really nice. Now, the Venus-Sun distance is about, well, roughly twice that of Mercury. It's about twice as far away. It's 0.72 of an astronomical unit. It's 67 million miles away, so about twice the distance of the Mercury-Sun distance. Well, why is Venus hotter? Well, it has this very, very thick atmosphere, which you can sort of see in the images. It's hard to see because you can't see through it. The atmosphere is so thick. And what that does is actually creates a greenhouse effect. And we're going to talk about that in a second. But a greenhouse effect for an atmosphere is basically the atmosphere helps keep the heat it absorbs, the radiation it absorbs from the sun inside the atmosphere and warms it up. Now, Earth has a greenhouse effect, and in fact, at the moment, the greenhouse effect might be working a bit too well, because that's what global warming is. But even if there was no global warming, if the Earth didn't have a greenhouse effect going on because of the water vapor and carbon dioxide, principally in the atmosphere, we'd be a frozen planet. We'd be a big ice ball, actually. So we do need a little bit of greenhouse effect just to keep temperature stable for biological systems on our planet. Okay, well, let's have a look at that in a bit more detail. Sorry, I'm just going to just rearrange across my legs here because one of my legs was sort of falling asleep there. So this graphic shows quite nicely, this comes from the European Space Agency, this graphic shows quite nicely what the greenhouse effect really is. And it's essentially when the sun's rays come into a planetary atmosphere, they heat the surface of the planet. Don't forget, the atmosphere of a planet is not directly heated by incoming solar radiation. It heats the planet itself, and then the planet re-radiates that heat as infrared. Now, if you have a sufficiently thick cloud deck, depending on what it's made from, that atmosphere can trap heat inside the atmosphere. Not all the heat will be re-radiated back into space. Now, let's have a look at what the Venus atmosphere is made from, and then that's going to give us a hint as to why it has such a strong greenhouse effect. So the atmosphere is very thick, as I said. It's actually about 90 times the thickness or the pressure of Earth's atmosphere. So whatever pressure we feel here at, say, sea level, depending on where you are in the world, on Venus, it's about 90 times as much. So that must mean effectively it's about 90 times as much material. So it's a very, very thick atmosphere. Well, here's what Venus's atmosphere is made of. The vast constituent of its atmosphere is actually carbon dioxide at the 96% level. So 24 parts out of 25 in the atmosphere of Venus is carbon dioxide. And then you have about 3.5% of molecular nitrogen. And then you've got a little bit of trace elements. You've got some sulfur dioxide, SO2. You've got a little bit of carbon monoxide, CO. You've got a tiny bit of water, H2O. A little bit of argon, a little bit of helium, He, a little bit of neon, a little bit of hydrogen chloride, and a little bit of hydrogen fluoride. Now, those last two molecules, hydrogen chloride, hydrogen fluoride, are very, very strong acids. And in fact, hydrogen fluoride is the strongest known acid that we have in the natural world here on Earth. And also the sulfur dioxide mixes with the water to produce sulfuric acid. So in actual fact, there is some sulfuric acid on Venus, there's some hydrogen chloride, hydrogen fluoride. The atmosphere of Venus is quite acidic. Now, of all those elements, let me just put, there is a rampant greenhouse effect. What I mean, rampant means it's very, very strong. The dominant greenhouse gas there out of all of those chemical elements or chemical molecules, chemical species, is carbon dioxide. Carbon dioxide, it turns out, is wonderful at absorbing infrared light. That's the heat coming off the planet, and then holding onto it, and it makes the molecule vibrate and rotate. Water's also very good at that in its atmosphere. Where on a cold winter's night, if it's ever cloudy, it feels just a little bit warmer because the water vapor in the clouds is re-radiating some of that infrared light that it's absorbed from the ground. that's emitting heat because it's the water molecules are vibrating and rotating. It's called low vibrational modes. Carbon dioxide has that too. And so all the big deal about carbon dioxide as a greenhouse effect here on Earth is very similar to that which is occurring on Venus, except on Venus it's vastly magnified because you have such a large amount of CO2 in the atmosphere. So that is why Venus is way hotter than Mercury, even though it's twice as far away from the sun and it's receiving 4 times less radiation than Mercury is. It's an inverse square law, so 1 over d squared. The greenhouse gases are trapping the heat and it raises the temperature to about 460 Celsius, which is knocking on the door of 870 Fahrenheit. In Kelvin, you just add 273 to that 460, which if I was to do it off the top of my head would be about 773 Kelvin in scientific terms. So there you go. That's why. So Mercury is not the hottest planet. It is indeed Venus. Okay, that's one of my faves. I realize I say it was one of my faves as every single thing I do, but I'm a bit geeky about this stuff. Here's a real big one. Now, you know, Joseph and I are part of the Event Horizon Telescope collaboration. We helped produce the first image of a black hole back in 2019 and all the subsequent images we have produced. So we are really into black holes. We're very sort of enamored by them. They're sort of very interesting to us. And this is a big myth that when you talk to people about the Event Horizon Telescope work that we have done, is they say, well, don't black holes suck everything up around them? How can anything be orbiting them? How can you detect the photons, the photon ring around the black hole? Well, it is a myth that black holes suck everything up. I'm going to leave that off for a second. This is a really great graphic from sciencenotes.org, and I really like it because they've put together all the major components of a black hole. So what is a black hole? Essentially, it's the object that's left over when the gravitational collapse of a star is so great, even what's left, the stellar remnant in the stellar core, like what stars are for low mass objects is a white dwarf. Slightly higher mass objects becomes a neutron star. But when the object at the center has so much gravity that it can't stop sort of collapsing in upon itself, that becomes a black hole. And typically it occurs for dying stars, and by dying I mean the stars are running out of their nuclear fuel. Happens when stars are about 7, 8-ish, maybe 7, 8, 9 solar masses. So 7 or 8 times the mass of our own sun. Any star bigger than that, more massive than that, when it does start to become, when it goes supernova, the stellar remnant left at the core, the gravity is so strong, it sort of collapses in upon itself, becomes a black hole. Well, a black hole has an anatomy just like everything else in the universe. It has parts to it. And this graphic shows it really, really nicely. So there's a really nice statement there that says, a black hole is an astronomical body so dense that even light can't escape its gravitational pull. Makes sense. However, that's only really near the very center. And we're going to define a certain part of this black hole in a second. But let's talk about the anatomy of a black hole. So the singularity is the sort of central point of that black hole, where the density is more or less infinite, because you've got such a massive amount of material and mass crunched up into a tiny, tiny space. So the density is just off the scale. Well, then you have these relativistic jets. What that means is you get these jets of material coming off black holes. And what we think they really are is they're sort of jet material that are carrying away some of the sort of spin energy of the black hole. Because we think if it were to collapse down to a singularity and it didn't have a way of getting rid of some of the rotational energy that it catches with us, that it took with it, it would just tear the black hole apart. So you get these relativistic jets coming out, and the relativistic means the material's moving close to the speed of light. And what that does is it takes away some of this rotational energy from the black hole, and it sort of stops it tearing itself apart as it spins. Well, the next thing that I think of the most important thing we should talk about is the so-called event horizon. And it's actually a sort of, it's not a real entity. It's not a physical place. It's a region around the black hole, and it's defined as the boundary beyond which nothing can escape, nothing, not even light. So if that's the black hole. Hang on, I keep getting confused with my hands here. Here's the black hole. The event horizon, let's say it's more or less where my chin is now. In this region, everything's going to get sucked onto the black hole. The gravitational attraction is so strong that not even light can escape. However, our side, our side of the event horizon, any material, photons, gas, dust, anything, it's still going to feel the attraction of the black hole, but the material will then orbit around it. It won't get sucked into it. And so what you're seeing here, you have this photon sphere where if it's photons, if it's light, the light will orbit the black hole because of the gravitational attraction. And then slightly farther out, you'll typically get what's called an accretion disk, and that tends to be hot, often millions of Kelvin, and it's made up of gas and dust. And some of that material can spiral onto the black hole. That's only if it goes past the event horizon. If it doesn't, it will just continue orbiting it. So black holes don't actually suck everything up around them. In fact, the very center of our galaxy, Sagittarius A star, there is a black hole there. It's several million solar masses, so it has about several million masses of our sun sort of in it. And there are some stars orbiting around it, in fact, very, very fast. And that's, in fact, how we know it's a black hole, because it's this very, very massive object when you can't see it in visible light. So it's like, can't be anything else except a black hole. And the reason why there are some stars orbiting at very enormous speeds is they're feeling the gravitational pull of this very, very massive object. So that's really interesting. So here's the formal definition of the Schwartzchild radius, basically the event horizon of the black hole. It's 2 times g is called the gravitational constant, so it's just a number, times the mass of the black hole divided by the speed of light squared. So c squared. C is the usual physics symbol for the speed of light. So you can actually work out where the event horizon is for a given black hole if you know its mass, m. And you can work out the mass m, not super precisely, but you can work it out to 10%, say, if you can, say, find some stars orbiting the black hole, and you can do some Keplerian orbits, some Newtonian physics on it. Otherwise, it's quite hard to measure the actual mass of the black hole. But you can still guesstimate it from mathematical modeling. And what that means is you can work out where the Schwarzschild radius is, the event horizon, and it turns out to be really quite close to the black hole. And remember, anything inside that radius does get sucked in. It gets gravitationally attracted in. It's not going to escape, even light. But outside of it, material can not only escape, but it can orbit the black hole itself. So really big myth in astronomy. Do black holes suck everything up around them? Inside the event horizon, yes. Outside, no, they do. No, they don't. The material orbits the black hole. Alrighty, what's next? Oh, so this is a funny one. I made a really nice slide deck for this. This is really nice. When I was researching this slide deck for today's Astro myths, I found a sort of another myth in the myth, and I'm going to talk about it because people like me and Joseph, we do these astronomy podcasts, and we talk about things like astronomy myths. And there are of course other people doing these types of podcasts, some of whom are astronomers, some aren't. They're sort of members of the general public, just very interested in science. And I've watched a few of them just to get an idea of what other people are doing. And there's a myth in the myth, and then we're going to talk about that. Okay, so first of all, is the sun a big yellow ball of fire? Well, let's just address that directly. This is what the sun looks like now, or at least the sun's regions as well. Now, this is a beautiful image from the SOHO satellite, which is a collaboration between NASA and ESA, and some ESO is the European Southern Observatory, so there's some astronomical ties there with both of those space agencies. These 4 images are really cool. Now, they're all different colors. So do we believe that some of the sun is yellow, some of it's green, and then the outside of it's red, and then the really outside of it's blue? And the answer is no. These are specifically color-coded for media releases by NASA and the European Space Agency. However, the sun is more or less yellow. It's sort of yellowy green, actually. So let me describe these images in detail, and then we'll talk about why it's that yellowy green. So the top left one here, this sort of one that looks like an orange from Sevilla in Spain. This is looking at the surface, or the photosphere, which we also define as the last scattering surface. And the big black arrow is pointing to a huge sunspot group there. That's very beautiful, actually. So this was taken about 25 years ago. So it would have been, at the last, two solar maxima ago. So it's definitely a solar maxima when you get lots of sunspot groups. Now, when you look at the sun, well, you should never look at the sun in the sky, of course, but if you ever sort of glance at the sun or you have a picture of it, it does appear yellowish. And that's a reasonable representation of it. There is a little bit of scattering by Earth's atmosphere, but you're seeing a lot of the rays coming directly through the atmosphere to your eyes. It's not far off yellow. The green image here, the one next door to it, this is actually, I think it's, just trying to judge from it, I think it's either extreme ultraviolet or very low, it's low energy X-rays or very high energy ultraviolet. It might, in fact, the image might be straddling the boundary between them. But this image is taken from, again, the SOHO satellite, and it has ultraviolet detectors on them in various regions, including soft X-rays, low energy X-rays. And what you can nicely see is not only you see the sun is in fact a circle, it is you're seeing these very bright active regions, and in fact what's going on there is there's some very, very high energy physics going on to create X-rays or extreme ultraviolet radiation. Now I did a lot of my PhD on this, so this is sort of right up my alley. Let's stop there for a second. Is the sun a ball of fire? Well, it isn't. It's not on fire. Don't forget, space doesn't have any oxygen. It has almost nothing in it. But so there's not enough oxygen to sort of create a fire. The energy coming from the sun is actually being created by nuclear fusion, and we know that now because of the sort of this work over the last 150 years or so, where we were able to calculate that the energy process on the sun couldn't be chemical. It couldn't be due to gravitation, just the fact that gravity's crunched up a big bunch of gas. There's enough energy for about 25 million years as it happens, but we know from the fossil record that the solar system is way older than that. And now with radiocarbon dating, we can measure the age of meteorites that hit the Earth, and we know that some of those are giving us levels of about 4.5 billion years of age. And so we think the solar system's 4.5 billion years old. What that means is chemically and gravitationally, there's not enough energy to keep the sun going, and we now know it's nuclear fusion. All the mathematical models with nuclear fusion do produce the energy levels we see from the sun. So it's great. So it's not a ball of fire. It's not yellow. Just in case you're interested and you want to go to the SOHO site for NASA ESA, the SOHO spacecraft is SOHO, and you see these beautiful images down here on the bottom. The one on the left here bottom left is showing a coronal mass ejection. In fact, it looks like several of them, where the outside of the sun is having these big explosions and throwing off matter, breaking open the magnetic fields, which you can see as these sort of loops here. Really very nice. And then this one here, the blue one, very fascinating image. It's very similar to the bottom left, except now it's zoomed out. You're sort of farther away. And what essentially you're seeing here is this is a sort of like an occulting, what do they call? I was going to make sure I get my nomenclature right here. It's oh my gosh, I forgot the word. It's basically the arm here. There's a very faint arm you can see down here at the sort of 7 o'clock position, and it's holding a disc in place over the surface, over the apparent surface of the sun. It's blocking out the light, so you can see what's going around, what's going on outside. And again, you're seeing this big sort of flash of material being blown out from a coronal mass ejection. It's called a coronagraph. There you go. Thank you. Thought of it in the end. A coronagraph allows you to see essentially the sun's corona, which is the very outside of the sun. Again, you're talking about 2.5 million Kelvin, and that's where these coronal mass ejections are coming from. And so the coronagraph allows you to see all of this material being blown off the sun when you have these big, enormous sunstorms and flares that are given off that normally, not non-normally, occasionally result in beautiful aurora that you see in the sky. Okay, so let's have a little think about the sun. The sun is, the surface temperature is 5,800 Kelvin. In science terms, that is for humans, that is about 5,500 Celsius or nearly 10,000 Fahrenheit. Now, I did tell you that the sun is not exactly yellow. We'll talk about that in a second, but it's approximately yellow. Now, what I'm showing you here on the left, this is a very, very important diagram in astronomy. It's called the HR diagram, a Hertzsprung-Russell diagram. And what it's really showing you is where you can expect stars to be based on their luminosity and their surface temperature. Now, on this graphic, the sun's position here, just slightly off center in the middle, is luminosity of 1. That means there's 1 solar luminosity. That's the brightness of the sun. And it's about 6,000 Kelvin. And so you can see, if you go all the way down, it's sort of in the yellowish part of the spectrum. Well, then you're seeing there's some sort of other areas here. But if you have a look at stars similar to the sun, they lie on what's called the main sequence. Now, if you remember, I used that phrase before, but the main sequence is essentially a spectral classification of a dwarf, a V. So if you remember Sirius is an A0 dwarf. Now, A0, I told you A0 is a surface temperature of 10,000 degrees. And so A0 is about here, just below the word sequence, the main sequence. If you go off to the left, it looks like the object is about 10 to the power 2, roughly. Is about 100 times brighter than the sun, a little bit less. That's because the surface area of that star is much bigger, because the A0 star is just physically bigger. So now we can start to see stars that are very, very hot, up to 30,000 Kelvin, are up here in the top left because they're very, very luminous. They're very big, physically big stars, big surface area, and they're hot. Come all the way down the main sequence, you get to the sun. It's fairly cool. And then as you go to the bottom right, you get these yellowy red objects that are much, much smaller than our sun. As you can see here, that can be between a tenth and a hundredth times smaller, and their surface temperatures can be as low as 3,000 Kelvin. Those objects are very red. Well, our sun is approximately yellow. Now, I say approximately because we'll talk about it a little bit. Its spectral type is G2V. The V's a dwarf, remember. So our sun is a G2. So we call it a yellow dwarf because it is about yellowish and it's a dwarf. Remember, the V is a dwarf. It's a main sequence. So a red dwarf, you can think of down here in the bottom right part of the Hertzsprung-Russell diagram. Dwarf doesn't have anything to do with its size, by the way. Dwarf just means it's on the main sequence. You can get a main sequence dwarf way up here, like Sirius. Where do we say Sirius was? 10,000 Kelvin. So it's about, well, it's not 100, but it looks like it's sort of 40 or 50 times bigger, maybe a bit more, 50 times bigger than the sun. It's still a dwarf. The V, the A0V means it's a dwarf. However, because there is some scattering in the Earth's atmosphere, the sun probably isn't yellow. It's probably more like yellowy green. And that's partly because there is some scattering of light away from our eyes by the atmosphere. Here's the double myth, like a myth of a myth. When I was doing some research for this video, everyone kept saying the sun isn't yellow because the Earth's atmosphere is doing all this distortion. The sun is actually white. Well, that is actually not true. So that's the myth part. And I found, like I said, 5 or 6 sources for this because I was doing some extensive research for this slide deck. And they kept saying, "Oh, the sun's not yellow. It's a myth. It's the atmosphere." That's not true. It's not. The sun is not white. And the reason why I know that, did I put it in here? No, I didn't. The reason why I know that is I know the spectral color of the sun, that its so-called B-V value is 0.6. That means it's got more light in the redder part of the spectrum than the bluer part of the spectrum. For a star to be pure white, as in the radiation is the same in all the different coloured filters, if you remember, I told you it was by definition A0. And so an A0 star has a surface temperature of 10,000. So in fact, a white star would actually be about here on the main sequence. Our sun is down here, more yellowy, and in fact, it's like I said, so yellowy green. If it was a much cooler star, it would be down here, and it would actually be red. It would be a red dwarf. And so something like, what would be a good example of that? Proxima Centauri, the closest star to the Earth, or to the Sun, is Proxima Cen. And Proxima Cen is an M5 dwarf, I believe, M5.5. So that's a very low mass object. You are probably talking about a 3000 Kelvin object star. So it, in fact, is very, very red. Okay, so this myth about the sun being white is not true. It is yellow, but probably more like yellowy green when you take into account Earth's atmosphere. So anyone tells you that, oh yeah, you take away Earth's atmosphere, the sun would look white. It actually does not. It's not hot enough to look white. So for a star to look white, all the radiation in all the different wave bands of the rainbow, so red, orange, yellow, green, blue, indigo, violet, have to be identical. And then when you combine them, you get white light. So that we don't have that for our sun. We get more light coming out in the redder part of the spectrum. So yeah, that was a sort of really nice part of astrophysics. When I thought about it, the more I heard about it, it's like, the sun is not white. What are we talking about? So there you go. That was just my own sort of pet peeve of the myth of a myth. All right, let's do one more. The Earth is flat. So this is just silly beyond means. And so I think if you remember from last time we did a podcast about 10 days ago, in fact, we actually put out a competition, a challenge. We'll give you $1,000 if any flat earther can sort of give us evidence to show that the NASA images of the planets are fake or not round. We'll provide that. We'll pay out that flat earth person saying, hey, you've proved us wrong. Our money's quite safe because it's just a complete myth that the Earth is flat. Now, I do realize there's some flat earthers that take this quite seriously, but all the evidence, all the scientific evidence is against them, just sort of completely. And I'm going to give you 3 main points, and I think you probably all know this already. But here are the 3 main sort of throwbacks against flat earth people. So, ships over the horizon, and again, I think this video link is going to show, or hopefully it's going to show up on the video. But this is a nice YouTube video I found of a cruise ship going farther and farther away from the observer. And what you're going to see is the ship becomes smaller and smaller, and you're seeing less of it. What you're really seeing is the ship is going over the horizon of a spherical planet. So let's just playing one more time as it's going over, it's getting smaller. There, right now, that you start to see the horizon effect. That's the spherical surface of the Earth that you're seeing there. So that was a really nice one. I really liked that video. So we, like I said, did the cruise ship. Okay, let's get rid of that. Next, there are real photographs, both from NASA and people who are astronomers or amateur astronomers, who take pictures of planets all the time. Now, I found this really nice montage of Hubble Space Telescope images on NASA's website. And as you can see, let's start with Jupiter, the biggest planet in the solar system. You've got 3 nice images here from 2015, 2019, 2024, the beautiful red spot there moving. Because, of course, Jupiter rotates. Jupiter looks perfectly round. It looks about as round as you can get, actually, which makes sense because it's so massive. There's gravity pulling all of its constituent parts toward the center equally. We saw images earlier on of Mercury and Venus, both from NASA spacecraft. Those planets looked also very, very round. We have Mars images that look the same. I don't have a Mars image here, but if you look at this is a really nice montage or collage of Saturn going from 2018 to 2024. The ring system is actually flattening it out as it moves in its as the Saturnian system moves in its orbit around the Sun. This is actually just a gorgeous montage of the ring system moving. But of course, as you can see, Saturn looks round. So now we've got Jupiter looking round, we've got Venus looking round, we've got Mercury looking round, and then on the top left, top right, we have Hubble images of Uranus and Neptune, and guess what? They're round. So you have to ask the question, if all the other major planets in the solar system are round, why would we be the only one that isn't? It's fairly illogical, or Occam's razor. The simplest answer is often the correct one. Occam's razor says that if all the other planets we can observe around the orbit the sun are round, chances are we are round too. It's not definitive, but it's certainly indicative. And then finally, lunar eclipses. A lunar eclipse is when the Earth gets between the sun and the moon directly in a straight line, and the sun's rays that are illuminating the full moon are blocked by the Earth getting in the way. I took this picture in 2022. I think it was the 8th of November, if I remember right there. I think I took it off the deck. I used to have a house up in Gloucester there at the top. And this is an image I took of the lunar eclipse. And as you can see, the shadow going across the Earth, the moon's surface there is curved. And that makes perfect sense, right? Because if you have, well, my hand isn't spherical, but if you have, well, how do I do it? I'll do it like this. If you have an illuminated object like the moon, and the eclipse comes, and if the eclipsing object is the Earth, if the Earth was flat, you would see a straight line going across that full moon. The very, very fact you see a curved surface and what looks like a curved shadow going across the illuminated moon means that us, the Earth, which is doing the shadowing of the full moon, we have to be curved as well. So the flat Earth theories don't work out, even from just these three basic empirical observations of either the Earth, of the solar system, or of the moon during eclipse. We can just prove beyond a reasonable doubt that flat Earth is probably not a viable scientific explanation of the shape of the Earth. Okay, so that's about it. I just wanted to put together a couple of astro myths that I had heard from friends, from some people who send us in questions on our Astraveo channel, and when I taught in schools. These are some of the questions that have come from school children. And they often have really good minds. They really put their questions together very nicely. If you want to if you'd like to know any more information about the myths we've talked about today, please drop us a line in the comments below. And if you have any other astronomy myths you think we should be busting and just disproving with pure science, let us know. Drop us a line. We'll be very happy to hear you. As always, thanks for watching, and keep looking up at the sky and enjoy yourself out there. All right, ciao, bye, good night.